Um, so I'm going to talk about this library called Patterning, which, as I've mentioned, is kind of my first Clojure stuff I started doing in 2014. And it kind of came out of my interest. So I'd been doing what is now generally called creative coding since I was at Goldsmiths, and I'd been doing some stuff in processing mainly. That's one of the reasons the name is patterning. It's kind of influenced by that way of describing things. And so I'd been doing a bit of that, which is Java, and some stuff in JavaScript and CoffeeScript as well at the time. But then in 2014, I wanted to get into something more powerful and understand functional programming better. So this was my sort of first library. I started then. And I presume, like I said, I would kind of like to say, does anyone want to ask anything about what creative coding is? But let's assume that you've probably heard of people doing these sort of interactive or generative artworks in various contexts. And for a long time, processing has been the kind of standard for it. It started off as a framework in Java combined with an IDE that makes it useful or easy to use, and then it has now jumped to JavaScript as well, and the browser, it's called P5 on the browser, and you can find out more about that. But okay, so I was kind of thinking about applying functional ideas to this creative coding, and particularly thinking about declarative patterns. In other, so my interest, the sort of patterns I liked at the time, I was very interested in, and I liked very much Portuguese tiles. Right, if you go around Lisbon or somewhere like that, there are very beautiful tiles in the walls. Some of them are sort of geometric patterns of various kinds. I mean, they also have some ones that are more just tiled walls that are representative paintings, but I was interested in the more abstract patterns and the kind of things within things that when you put a number of them together, you get a sort of emergent, larger thing out of it. So I was just really was thinking, how am I going to represent this functionally? And of course, that's actually quite obvious what you're going to do if you've got a functional programming language. You're going to have a function that returns some shapes, and then you're going to combine those and compose those together with other shapes and just build it up. So it's sort of an obvious way. There's an obvious parallel, I think, between the sort of the functional thinking and the sorts of patterns I wanted to do. So I'm going to take you right now through the basic things that are in the patterning library. And then I'm just going to explain, I'm going to show you the code, I'm going to show you what they draw, and they're going to start very simply, and they're not going to get hugely complicated. And then I'm just going to talk a little bit more about some of the things I used them for in terms of artistic works, and sort of where I'm going with this as well. So let's talk about what the elements of patterning are. Well, patterning is just really three sorts of things. There's what I call the S shape or styled shape. And then a styled shape is literally nothing more than a vector of points and a style. So points are just it's all 2D. There's nothing currently in patterning that's a three-dimensional. So I've kind of thought about taking it in that direction, but my brain doesn't think very well in 3 dimensions. So it's not an area I've gone very far into at the moment. So everything is going to be 2D here. So an S shape, you can think of it as rather like a path in SVG or something like that. You've got a number of, just a list or a sequence of points, and you've got a style that's applied to it. And styles have these three elements that are very common. If you've ever done anything drawing onto the canvas, or you've used SVG, or you've done processing, you've got a color for the line that's being drawn, which is called the stroke. You've got a color for a shape that's filled, and often you've got the sort of thickness of the border around the shape, which is called the stroke weight. So that's something you get in processing, and I just copied that idea in patterning. So you've just got a map that's basically two elements: points, which is the list of points, and the style, which is the map of these. It's got some other style things as well, but those are the three main ones. Now, then there's just what I initially called group, which was just a list of S shapes. Now, unlike the path in SVG, for example, in the path in SVG, you're drawing a line from one point to another, or you can actually jump, so you can have disjoint things. In patterning, shapes, S shapes, are always continuous. In other words, there's no ability to jump from one point to another. You've just got a sequence of shapes, and we're going to draw lines of points, and we're going to draw lines between them all. If you want a shape, something bigger, which is made of discontinuous areas, you're going to put it into what's called a group or a pattern. So patterns are the fundamental things that all patterns are made of, and they're nothing more than a list of S shapes. It's a flattened list. So one of the features of patterning is that I don't keep the hierarchical structure. I decided to flatten it completely. Now, that's kind of turned out to have some pros and cons, but on the whole, for my usage, I'm quite happy with that. It sort of makes some things easier, but possibly there are times you might lose something from that. But anyway, so that's all you've got. You've got shapes, S shapes, patterns, or groups, which are sequences of S shapes. And then the final thing is layouts. Now, a layout is just a function that takes one or more patterns or sequences of patterns and returns another pattern. Right, I hope everyone is following this, and that wasn't too much to dump on you. So let's look at like a simple pattern in patterning. What I've done is I've just set up these slides here. All these patterns are being drawn, but we can't actually interact with it here. There is an online tutorial site, which I'll show you a bit later, where you can actually go and play with patterning by editing the code in the thing. At some point, I'll make it look as nice as this, because this is starting to look nicer than my current online tutorial site. But here's a simple polygon. So poly is just one of the standard functions in patterning to give you a polygon shape. It takes these arguments, that's the X and Y of the center point. It takes the radius, and it takes the number of sides. And so this is a pentagon, it just does that. And then finally, it takes the style. As you can see, a style is just a map with a stroke value and a fill value. And those are colors. Now, there's always a bit of a question when you're representing, how do you represent colors? I mean, a lot of graphics pipelines or graphics layers or frameworks already have their own representations for points and colors and things. I really wanted to keep patterning independent of any particular platform. So it's not it's not reliant on Java. It's not reliant on JavaScript. It's not necessarily a web thing. The entire representation of these patterns is abstract, or it's just data structures. And then when it comes to drawing it, then there's a function that goes and draws it. This particular one is drawing on the HTML5 canvas. So we have to represent everything. Points are just numbers. This function p color literally just produces our representation of a color, which you don't need to think about, but I think it is just a vector. And so this is it, the simplest sort of pattern you can draw. Call the poly function out of the standard library, give it a center point, give it a radius, give it 5, tell me how many sides it is, and give it its styling information. So what can we do once we've got a pattern or a group? Because this is not simply now an S shape. I mean, there's really only one S shape in it, but it's already been put into this list of S shapes to make it a pattern as the data structures. Well, we can now start passing it to one of these layout functions. So one of the layout functions we've got in the library is this thing called ClockRotate. So all that ClockRotate does, as you can imagine, you give it a pattern, an existing pattern, and a number to repeat, and it just gives you that number of that pattern. So here's the poly inside being defined here. It's got a center. Okay, so the coordinate system for patterns. The other thing is, because we're going to be putting patterns inside patterns inside patterns, it's got to have an abstract coordinate system, and so every pattern is always written in a notional space that goes from -1 up here to +1 down here. So it's always a square. We expect the entire pattern to fit inside a square that's 2 by 2 with 0, 0 at the center. So that's the conceptually, whenever you're thinking of coordinates, you never have to think about the actual size on the screen, or because that's going to start changing as we start combining things and moving them around and shrinking them and stuff like that. So it's always in this virtual coordinate system of -1 to +1. So at this point, this poly isn't centered on the center. It's offset at 0.5, 0.5, which puts it down here somewhere. In fact, it's not a big, it's only a 0.3 as its radius, and it's a triangle, okay, with its styling. But then we pass that into the ClockRotate function, and we get back this shape of all, which I hope is obvious. So what can we do with this? Now we can stack. So the next layout engine is actually this thing called stack. So it's a composition or compositor engine. It just puts one thing on top of another. So the first one was this ClockRotate. The second one, we could just take a pattern here. I'll just scroll off, but that's a very simple polygon. That's just this blue pentagon. And then we can stack that on top of the ClockRotate here, which you saw previously. So these things just nest and stack continuously. I hope that makes sense. So then we've got some grid layouts. Now, I'm not going to show all the grid layouts we've got, but the sort of standard one, you just give it again, it's another layout function, and you can give it the number of things. Everything is always a square. There are some ways to get things that are not squares in patterning, but effectively you do it by either stretching things or sort of putting a kind of letterbox around it to kind of clip out all the things that you don't want. But by default, if I take any particular pattern, I feed it into a layout, I'm going to expect that the next layout is coming out in another square of the same dimension. So this one is just a 6 by 6 square. Now, the thing that's important to note here is you don't just, with something like a grid layout, you don't just pass it an individual pattern. What you pass it is a stream of patterns, because it really is the layout that's going to decide how large it is. So in this case, all right, the function's got a 6, so we know it's a 6 by 6 square. So we've got to give it enough patterns to fill that square with. So we don't just give it a pattern and say always repeat this pattern, because we're going to be able to do some tricks with that stream of patterns in a second. But so if you wanted to just say fill the entire grid with copies of the same thing, we're just going to use the standard Clojure repeat function here to take that pattern we generated with this stack and send that through. There is a thing here called checked layout, or like the checkerboard layout. So this was a standard library layout that just makes grids. This one, you pass it 2 streams. In this case, we've defined the triangle and the pentagon. We've just made it to give it 2 arguments. Which is a 6 by 6 grid. We're going to repeat creating two streams here. It very, very much relies on the laziness of Clojure. This is one of the kind of joys of writing Clojure for me, and particularly doing this sort of thing in Clojure, is that you do just like create these infinite streams of shapes, and then you can just sort of pipe them into these layouts, and the layouts will use as many as they need. So the other thing that's slightly weird here is, on the whole, we tend to fill things in vertical stripes rather than horizontal stripes. You can turn that around, but by default they do that. So yeah, it takes a pentagon, then it takes one of these other things, it takes a pentagon, one of these other things. Okay, another sort of standard thing we've got is this thing called a drunk line. So a drunkard's walk is when you start in a particular point and then you move forward in a random direction from that point to another point, then you move forward in a random direction from there, and another from there, and another from there, another. This should be straightforward. So we have a function called drunk line, which allows us to make a line of a certain number of steps of a certain length, again with a style. And as you can see, it happens to make that. Now, if I just reload this, you'll see that the shape of that line keeps changing. So inside the drunk line function, there is some randomness. Now, later on, you'll see, I mean, initially I put lots of random. I thought, what's the harm in putting randomness in? Recently, I've been kind of working through and trying to take randomness out, or at least make randomness a parameter, or a random generator, a parameter, so that it can be, even these kind of allegedly random things can be run deterministically if you need them to be. So a drunk line is just a sort of thing, and that's quite useful if you just want to make some nice patterns with that. Like you can put the drunk line into the ClockRotate, and again, every time you load this, you're going to get a different shape. Again, you're just stacking these things together. We've got Bezier curves. I've never actually done much with Bezier curves, but again, they were the underlying. In this is one case where, because the underlying ways I have of rendering it can do Bezier curves, I thought, why not? So a Bezier curve is a curve that's defined in terms of 4 points. These are not coordinates, or they're not coordinates of the elements of the curve. They're coordinates of the end points of the curve and two sort of control points of this line, and it draws this smooth curve between them. Like I say, I don't actually use that very much, but it is there in the library. So here are a couple of the more complex layouts we've got. I'll just show you some of these. These are built into the library, although I've taken some of the code just to show you how it works here. So this is a framed layout. Now, what's going on here, this is a layout that takes 3 arguments. The first of these arguments is a stream to fill these corners of the frame. You could just give it an array of 4 different things, or a vector of 4 different things, but I mean, you can give it an infinite stream as well. The second one is the stream that's going to fill up these edges here. And the third one is a single pattern that's going to be the pattern in the middle. So just as the previous things here, you give it a size, 6x6 grid. This is notionally a grid of in this case 7x7. There's 7 items across 7 columns and 7 rows, but it's laid out with 4 corners, the edges plus the thing. So here's just an example of me building that, and the only the code, the call is here on the framed thing there. We can write here. We've got a thing called nested stack. What nested stack does is actually, and it does several things. it draws the same shape inside itself, shrinking. The way it does that is that it applies different colors to those, and in fact you've got a way of you've got your shrinking function, or your whatever in fact you want to do with it. So when you call the nested stack function, the first thing you've got to give it is a stream of colors here. In that case, this color setup colors does this for us. So the shape we gave it was this shape called simple diamond. The shape is defined up here, this simple diamond. So as you can imagine, it's a simple diamond. It's just a shape that's got a color. Yeah, sorry, it's a diamond shape. It's a square on its side, in its corner. That's all it is. Comes out of the standard library of. There's a lot of basic shapes in the standard library. We define a couple of these colors here. Then we define this thing here, which is setting up a kind of stream of colors. And then we pass in, as well as that, to the nested stack, the original shape. And then we pass this, and this is kind of more interesting. This is the reduction function, or the reducer function. I'm not a reducer in basically what we're doing is every time around this, we're it's like iterating in Clojure, isn't it? Yeah. I mean, every time we take the original shape and we apply this to it, which is just a small shrinking in this case, to values, and at the same time, the nested stack maps these changes in color across it. Finally, I'm going to show you the shape as the S shape as layout. So a shape is itself just a sequence of points. Remember, the shape is the fundamental shape that everything, the things that these are built on. So we can write now. This is in the standard library, but I'm showing a couple of bits of the implementation here. This shape to positions function is just literally pulling the points values out of the shape, which is just a map of key, with style and points. Then shape as layout, as I say, that isn't the standard function, but here it is. We just basically extract the points from it, from the shape we gave it. And we map a shrinking, again, so scale is just a function that that reduces shapes, makes them smaller or bigger if you prefer. And we're just taking that function with a standardized argument, passing it or mapping it across this group stream, which is the things that we're going to. I mean, the purpose of this layout is just to take an existing line, which I hope you can see sort of underneath the. It's a drunk line, so just a random line, and we're just taking the points that made it up, and we are now just using it as a layout to map these squares across. We've got a randomized color function, so we're inside the shape as layout. We are taking the shapes, the patterns, and these patterns can be as complex as they like. Everything is composable, right? So they could be as complex as the most complicated pattern you've seen, shrinking it down and just mapping it across and these points of the drunk line. We draw the drunk line there. We map a random color to each of them as well, and then we call that. Right. Yeah. So the main functional trick is because we're passing lots of these sequences and of patterns into a lot of these layout functions, it means that we can map various things across them. So here, for example, we defined a thing called an A round. It's just a thing that is a ClockRotate, a sort of bouquet almost of polygons. with a color, a color for the border and the fill color. As you can see, we've got transparency here for some of our colors. We have a transparent color just by having a fourth parameter to the p color function, and that's just like all the other colors. It's 0 to 255. Same with the transparency in this. So the A round is just a standard thing that draws one of those. And then the pattern just says we're going to take a grid layout here, 4x4 grid layout. But what we're going to do in this case is we are, instead of just repeating a thing, we're going to iterate. Okay, so this is something that standard Clojure again takes an initial value and then does something to it. We take the p scale function, so that's actually the function. The scale function is just the function that resizes, shrinks in this case a pattern. We're just using partial and the 0.9 parameter to make a function that does nothing but shrink things to 0.9 of their existing size, and then we give that we apply that to the A round that we created initially as a 9-sided. It's a bouquet of 9-sided polygons with the initial color. So what happens, as you can see, we then put it into the grid and it's just shrinking down. Okay, another thing we could do, for example, is we could have a random turn layout. So again, this is in the library, but I've pulled some of the code out just for you to see how it works. First thing is we just define a bunch of these things called Q1 rot, Q2 rot. These are things that take any pattern and just rotate it 90 degrees. Or one is 90, one is 180, one is 270 degrees, or half pi and pi and 2/3 pi times 3/2 or whatever. So each of them is just a function, rotate that by that. Then we just have a function here called random turn groups, and all that's doing is again, group is like the original name for these lists of S shapes, which are the patterns. I've kind of thought of changing that name in the library, but it's a bit established now. This is the problem. To actually change it, I would be breaking any existing patterns that are written, including some of my own. So maybe there'll be a breaking change to the library at some point that will change that. But all we're doing is we're just doing a random. We're basically choosing a random rotation to each thing, and again we just map that random turn onto the groups. So what are we going to get? We're going to end up with if you pass it a stream of patterns, you are going to get back a stream where each of them is rotated either by no degrees, or pi over 2, or pi, or 3 times pi over 2. Or in fact, I just did it the other way around. I just subtracted it. So here we just make a set of this shape here. You can make an S shape with that, which is just like a triangle. So these are, I can't remember the name of these things, but these are the tiles that they're just basically half dark grey, half light orange, or half black, half white. And of course, every time we reload this page, we will get a different shape appearing there. So this is the classic thing you want to do with tiles, really, is play around with what emerges when you do some interesting things. There's a kind of research group called Alpaca. I don't know if anyone's come across that, which is the algorithmic pattern group. They're kind of they're very associated with people who do live coding and music, and they're sort of based by the guy that's who wrote Tidal Cycles, which is a live coding language for music. He runs it out of Sheffield, and they had a big conference about 2 years ago, and there was a very interesting talk on this sort of pattern there that was sort of it was a French architect or something from the sort of 17th century who came up with a notation system for parquet floors or something, and used the kind of notation ways of representing complex patterns of floors with that. And I have actually done some experiments, unfortunately I don't have them here, where I've used his notation system with this kind of principle to make more structured complex shapes out of these. But unfortunately I didn't think, I'm only thinking of this now, I didn't think of doing it for my all right, yeah. Okay, and we can sort of map multiple transforms. I mean, map is just a function that has got, that can take more than one set of things you're mapping across, right? A stream. So at this point, we've got we've got a random color function again, and here we're just making a grid layout, and this time we're mapping random color across. Okay, mapping the rotate function, and the rotate is a function on patterns that just rotates them by a certain amount. So what we've done here is we've basically taken this partial, we're taking plus, and we're making a function where we add, that just adds 0.2. So this is becoming a function which is rotating the shape by 0.2 radians, right? Starting with 0. So iterate is just basically, yeah, doesn't matter where it's starting here. And then we've got another function here, which is scaling by 0.97, so just shrinking the pattern down a little bit. The pattern is just this triangle with a line through it. And because this is Clojure and map can take multiple things, we can basically this is a stream of numbers, or a stream of functions adding 0.2. It's going to this rotate function here. It's becoming the first argument to the rotate function. This is the stream of ever smaller versions of this object, of this pattern here. That's the second argument to the rotate function, or one of those is. So we just map that rotate function across these two streams. I hope that's relatively intelligible. Even I'm looking at it now, trying to remember what I do. So yeah, we get that. The triangle change, and then we map random colors. So we get the color, the triangle changes colors, it shrinks, it rotates as it's going through the thing. Right, let's talk about a couple of specialist things here. We have a turtle. So a turtle is you know, the original sort of drawing thing from Logo. You know, originally it was an actual robot that went around the floor with a pen. It's become a different way of thinking about drawing. So drawing, okay, typically you have paths where you sort of think in terms of absolute points in a space, and then you draw lines between them. That's how most graphics things work. But a turtle is basically a kind of relative. You think about drawing lines with in terms of basically how far you go forward, and then what angle do you turn, how far do you then go forward, what angle do you turn. So I've got a function that, okay, so a turtle is a function that, standard function, you give it some parameters and it gives you back again a pattern, so just a set of things, but with the logic of a turtle, of starting at a particular position here. That's the initial position you start at. Remember, all the coordinates are always between -1 and +1. A length of the standard forward movement, and then sorry, the length of the standard forward movement in the X and Y coordinates, I think, if I remember correctly. I might have to check that. And then what is the standard turning angle that you'll make, either turning right or left? And then this is slightly weird. Then you go to string, and a string consists of F's, pluses, and minuses. An F just means go forward by the forward movement. The plus means rotate by our standard angle, and the minus means rotate the other direction by the standard angle. So, and then again, because it's a because it's the same kind of thing that everything else is in patterning, you give it a style as well. So this turtle here draws this kind of lozenge shape. There, it starts up in -4, -0.8. And it probably just goes this way round. So it goes 4 forward, that's this length, then one turn to the right, 1 forward, 1 turn to the right, 1 forward, 1 turn to the right, 1 forward, 1 turn to the right, 4 forward here, and similarly around there. So that gives you that sort of shape. And so anything that is easier to draw that way, you will, the turtle might be the right tool for drawing that kind of thing. Now, where it becomes a little bit more interesting here is in this second example I've got, which is a kind of, well, you've got a sort of recursive or ability to make what I call sub things with the turtle language. So the turtle string language, you can now see there is this square brackets here. So what happens with the turtle is it's going forward. Then if it hits this square bracket here, it's going to recurse down into a second layer. Now the second layer turtle, it's going to rotate a bit to the left. It's going to go forward. In fact, it's going to now go down a third level, rotate again, turn to the left again. Now it's actually going up here, going here, turning left again, going forward again. Then it hits the closing bracket. What does that mean? It means it jumps back to the last fork, effectively. Now it goes forward again. Then you get this, you get another closing bracket, you jump back to here, you now go forward up to here, and then you go turn to the right and go forward. So this is going to let you make patterns which have some kind of recursive or fractal structure. Okay, now as long as you build that into this string. Now, why are we kind of interested in doing things like that? Well, L systems. So an L system is stands for Lindenmayer system, I think. So Lindenmayer was a kind of researcher, probably a mathematician, I think, who was interested in rewrite rules and recursion, things like this. So again, I'm not sure how many of you are familiar with this, but these are actually quite standard things for drawing stuff that has a kind of biological or organic, floral, fractal kind of feel to it. So it's a rule, right? You've got a rule that says every time in the string we see an A, we're going to rewrite that with B and A. Every time in the string we see a B, we're going to rewrite it with C. So if you apply that to the starting string A, you're just going to, and you run it once, you're just going to get the string BA. If you apply it again to the string, now you're going to get CBA, because obviously that B turns into the C. Meanwhile, that A turns into another BA. Applied again, you get a CCBA, etc. So, as I say, in patterning, we use the L systems to feed the turtle. So I can call an L system with these two parameters, the initial point, and then the string of rules, rewrite rules. And what that's going to do is that's going to create a function that, if I remember correctly, that doesn't do it there and then. It creates a function which you then apply to the number of times you want to run it. So here is a pattern that's basically two plant shapes. Now, it's very, very common for people to use Lindenmayer systems to generate plants like this. This is a very common idea in some sort of computer graphics, and you'll find lots of examples. So what's happening here? Well, I've just did it twice with two slightly different shaped ones. The first L system, we define here, is just this pattern. Every F is going to turn into something like this. That's right. Every F. So this is this. There could be more than one rule here, right? In this case, we've only got one rule. The F turns into that long string. But this vector here, I could put a second rule and a third rule into that. What comes back from L system is itself a function, and the function, okay, we've called it grow here. And that takes two arguments. The 4 is the number of times we're going to run the rewrite rule, and the F is the starting position. So that's not the starting position. I was misleading you. That's the rule. That's the start, and the 4 is the number of times we run it. So that obviously produces the kind of string which is suitable to giving to our turtle. So now I have a basic turtle again. I give it a starting point and a length and an angle. And for the string, or for the movement it's going to make, I give it the grow function that came out of the L system. So the two are very much intended to work together. I mean, obviously you can use the turtle for all sorts of other things as well, but the turtle is sort of designed for working with an L system. Here is a second one, which I'm not going to talk too much about because I just noticed there is a bug here, and I'm not sure what the bug is to do with. So it's doing the same thing. It's possible to attach to the L systems things that will draw some other things at certain places. So basically some other drawing functionality, like when it sees this Z here in the final string, it's meant to call and draw this polygon. And for some reason in this version, I made the slide about an hour ago, so I just noticed it's not doing it. So it does work in many contexts. I don't know why it's not working here right now. I apologize for that. So one of my interests when I was at Goldsmiths, and sort of a background interest for me a lot, and I mean, this is where you were asking about Carsten Schmidt and his stuff with Clojure and sort of like making 3D objects for printing and stuff. I do have quite an interest in making things for fabrication. So just go back a second. I hope this is not too much of a self-indulgent diversion. This is a link to my site. When I was at Goldsmiths, I was writing code to generate these sort of machines that were laser cut out of acrylic. You know, you can see here what we did was we had a processing sketch that would let you design little fractals, cogwheels, and then the laser cutter would actually cut them out. I hope this is sort of clear. And then I would assemble them into these sort of machines like this, where the cogs would engage and you could do that stuff. So that code was a sort of artwork from that made things like this. It's all in processing in Java. So one of the things I've been wanting to do, and I've started doing, although it's not to that stage yet, is doing the same in patterning. So I do have some basic cog type things. We've got a make cog function here that takes a whole number of parameters. Cogwheels have quite a lot of parameters to define, like the circular pitch and the various sorts of pitches for these lengths of the bits of the cogwheels. In patterning, you give it these things. Whether you want a round or a square circle in the middle, that depends on whether you're going to make it engage, rotate freely on the axle, or if it's meant to be fixed to the axle. Then there is this function space engage. So basically here I've defined A as being a cog here, and then I've defined B as being the cog which is in a 2-to-1 ratio with that cog. And so that creates a second cog for me that has the right ratio of gears, so that when you turn, if they engage, one turns at the appropriate speed compared to the other. And then the pattern is simply stacking. In this case, I'm just drawing the two. I'm stacking them together, and cogs themselves are not patterns because they have to have some other information, but there is a cog to pattern function is standard in patterning that will turn them into patterns that lets us draw them. Those particular, oh, hang on, what am I doing here? If I were to just quickly, as I'm slightly being self-indulgent, here's my artistic site, but if I was to go to, this is the residency where I did that, you'll see here a little bit of 3D printing of those cogs, right? So those cogs were just 2D. I exported them as SVG files, and then I put them into another program, extruded them into 3D, and 3D printed those cogs. So it's kind of the aspiration. I'm going to build up towards doing more of this kind of thing, but currently patterning is not a 3D design software at all. You know, in the long term, I'm sort of hoping that I will be able to do. I'm kind of fascinated by the idea of being able to represent machinery again in this functional style. I mean, one of the things that triggered this is in back around 2010, I was given as a present like a children's build your own clock kit, you know, with just some plastic cogwheels and springs and motors and things. And one of the things that I hadn't really thought about a clock before, it never occurred to me because I'd never had any experience of this, is that it actually was a hierarchy. In other words, there was a sort of central thing with the spring unwinding, and everything else was just kind of coming out of that that hierarchical thing. You know, the hands were sort of downstream of it. You know, the movement was going from the sort of the central motor down to this, to which would end up turning one hand, and it would go a slightly different branch down the hierarchy to go to the other hand, and it would go to the escapement or the regulator that would sort of keep it. So because I was, you know, all of this thinking about patterns and all of this thinking about things is very much hierarchical. And, you know, like functional programming, Lisp programming languages are very much about hierarchies in this sort of sense, or things nested within other things, functions calling the functions recursively down to things. So I did kind of get very intrigued and inspired in some ways by that parallel between the between that, which is why I sort of have these ideas that, you know, like, could you not represent, let's say, a robot body one day effectively in code? And particularly thinking about it like take HTML or something. HTML gives you the hierarchical structure of a document, and then you've got CSS, and you've got a default layout for your document. Then you can use CSS to kind of change the shape. Well, could you more or less represent machinery as just a hierarchical document of this control, you know, this is plugged into this, this is plugged into this, and then afterwards try applying some extra styling rules to adjust the size and shape and ratios and stuff like that. I don't know. This is a background idea I've had for a long time, and I'm kind of always fascinated by and coming back to. But the extent to which anything exists currently, it's just in patterning does have the beginnings of some functions to represent cogwheels, and I will be working on other parts. At the moment, all 2D, but that's where 3D would become quite important. Okay, so I'm going to show you how am I doing for time, by the way? Am I going over time or am I under time?
Yeah, you are slightly over time.
Okay, right. So let's quickly just I was concerned. It was all going to be over in half an hour, so I'm speeding up a bit now. Okay, so I was going to show you a couple of examples of artworks I've done. Again, I was invited to an exhibition in Cheetah in Brazil, which was actually a kind of small rural town, and it was an exhibition about what's called Cheetah in Brazil, which is like a very kitsch floral pattern that's very common. You know, it's kind of on like plastic tablecloths in sort of restaurants or cheap restaurants, but it's clothes. It's a sort of folkloric floral pattern, and I was invited to be part of this exhibition. I was living in Brazil. I've been living in Brazil for a while, so I was invited to participate. Of course, most of the people were coming and doing textiles and things like that, but I decided to try and do live coding of the pattern. So I went to the exhibition, and it was in the evening. I sort of put up a projector, and I sat there looking at some of these other examples of this floral pattern, trying to figure out how to turn this into code, and you know, having it on a projector, and sort of people could see my attempts to do that. So this is kind of what I came up with at the end of that evening. So I was looking at the sorts of colors, these very bright blues and reds and greens and yellows. So I've got some definitions of those colors. I've got some functions like this random rotation, you know, again, this is done with, I'll come to the randomness in a minute. Just to say, this randint is an object that creates randomness that's passed in from the JavaScript, and I'll explain why that is in a minute. Then we make the inner parts. You know, it gets quite complicated, but there's nothing really here that you haven't seen before. It is all just, okay, diamonds, stretching them, translating, just moving somewhere around the thing, clock rotating them. We do all this, put it all together, and eventually you will come out with a pattern like this. And every time you reload it, it will be slightly different. Those little white flowers will move around, and the yellowy things will change their position. So nothing that you haven't seen before. Half drop grid layout is very similar to the other layout. It just staggers the two rows of things. The other work I wanted to show you is a thing that was called The City We Invent, which is not here. I couldn't make a slide of it. So it's a pattern that is a sort of grid of stylized bits of buildings, as you can see here, which is, again, I did this on this artistic residency. So it was designed to be engraved. I don't know if this is clear to people, and but what I did was I kind of made a lot of panels with laser engraving of these fragments of cities. Every time you run this, of course, you get a different. The city is a sort of set of random parts that fit together in this kind of exquisite corpse kind of way. They all have to. Each tile has to join the next tile at the same points. And it was kind of inspired a little bit by the architecture of the small village in Portugal and the things like that. But then I made like a whole bunch of these, all different random things, and sort of tiled them all together on the wall of the gallery in the exhibition I was in. So that's the thing. The other thing that's happened with this more recently, I was invited to be in an exhibition of what's called NFTs, which is what's called a non-fungible token. So a non-fungible token is something that lives on a blockchain. So if you know what a cryptocurrency is, you pass coins or money in the form of fragments of a coin from one person to another on a blockchain. Blockchains are very problematic. I don't want to they're an ecological and environmental disaster. But I was invited to be part of this exhibition, and they were using something called the Tezos blockchain, which is a much more low energy blockchain. So I felt it was reasonably, I didn't feel too guilty about that. If anyone wants to challenge me or talk about it, we can. So one of the interesting things about that is people are trying to use the idea of a blockchain to sell unique virtual artworks. Of course, you know, it's artificial scarcity. There's no real scarcity in digital things, but you basically, on the blockchain, you make, with an NFT, you make an artwork and you more or less kind of record into the ledger that's the blockchain, this person is the owner of this artwork. And then the artwork, you represent the artwork as the hash of the code that does it. So this is something we can talk more about. It don't know if people are interested or not. Just to say, it turns out there's this platform called FX hash. This is a place where people sell these things, and what they want from it is they want a deterministic randomness. In other words, they want something that's generative or random, but when you sell this, you might sell an edition of 10 of them. So they'll mint 10 records on the blockchain saying this is the owner of this pattern. But what they want is the pattern to be, each person to get a different pattern, but the pattern, the same edition of the pattern to look the same every time you see it. So, you know, if you buy a copy of this, then I mean, I can show you a random one it's generated. Now, this again is all generated. It's just ClojureScript turned into JavaScript. It's running on their site. Now, every time you can see different versions of it. Now, every time somebody buys one, they will get a version which is different from everybody else's version. But every time they then come back and look at their version, they will see the same thing. So that's enabled by this platform, FX hash, giving you a library in JavaScript, which is a deterministic random library. In other words, they seed the random number generator from the ID of the token that was used to buy it. Now, this one interesting thing on this, I just kind of gave a little Easter egg or hack to this. The clocks are now showing the real time. So in principle, it's gone to the clock of the thing, and the clocks are showing 7:45, which is the right time. So in order to work with this, I had to write my own wrapper in ClojureScript to make. I had to write my own wrapper to their random number generator to make my own thing. So here it is. It's a JavaScript library, but this is designed to fit a protocol that I defined in Clojure for a random number generator. And then what I've been doing most recently in the library is I've been going through all those places where there was randomness and making the random, basically passing in an object which is a random generator, which has these functions like random float, random nth, randint, random angle, so that if you want to use the library in this context of FX hash, you can create this object in JavaScript, pass this into the library. So I found a lot about that I didn't know that I suddenly found was much more painful in terms of how to interop between ClojureScript and JavaScript. I don't write JavaScript a lot. I don't like JavaScript at all. I want to write ClojureScript. So it was a bit of an education realizing that, well, basically I just didn't manage to make it work with JavaScript objects that implement the protocol officially. It just went into this like infinite recursion for some reason, so I had to give up on that. But anyway, that's something that's coming to the library. Is now parameterized randomness, so you can basically give it deterministic randomness. So nowhere in the main library do you have calls out to randint and things like that. You can now always send in there's a default randomness which does call those standard Clojure random functions, but now you send in a an object that gives that to you. So if you needed something like the FX hash library, there's a way of sending that. Or if there was some other need for a deterministic randomness in those patterns, you can have it. Right. Oh, yeah, I was going to show you the very last thing. Let's see if I can show you. Here in. So this is now Quil. This is the Clojure library around processing. And yeah. I've got the screen sharing thing. Right. So here is the code that's drawing that. So as people were asking, what processing does is it gives you some standard values like the mouse position and the frame count and stuff like that. So when you write a program in processing, you're writing a kind of setup program, and then you're writing a thing that's going to be a function called draw that gets called, you know, in principle 30 times a second. I've got it slower here because it's not that fast, but and in that function you can access things like the mouse position and stuff like that, so you can make reactive or evolving things. So here I've got a basic little function called map mouse. It just calls these things like the XY of the mouse. It also maps the XY of the mouse. What it does here is it maps the XY of the mouse on the screen into the coordinates the patterning uses, the -1 to +1 range. It also maps it between 0 and 1 because it's useful to have that. Width and height. And the frame count is just like a number that increments every time the frame continues. So inside a pattern like this, now I hope this is legible, the text a bit small here, but I've got a checked thing. I've got a thing I'm repeating here, which is a polygon, a standard hexagon polygon. But you'll notice I'm using the value x01, which is the value of the mouse scaled between more and 1. So as I roll the mouse over it, you'll see that these hexagons start appearing and getting larger and larger and larger. That's just mapped to the position of the x position of the mouse here. So all I had to do is in that function call to poly, I just gave that value. Same here. I've got the size being based on the frame count, and I've run it through a log function, so it kind of starts growing initially. It grows faster when it's smaller, and then it slows down. That's why I just put it through a log function. So as you can see, we can make interactive things there. That's a combination of patterning to do the drawing with the processing. Quil is the wraparound processing, giving us access to those live dynamic things. And yeah, these things are laid out in a standard grid, etc., etc. I've got well, I think I've kind of showed enough now, and I hope that's it. That gives you an idea of what patterning is and how it works, and questions and things like that. Thank you very much for watching. Sorry, I have gone on quite a long time now.